It may seem odd to begin a presentation about star formation by recalling the types of deaths that stars undergo. The reason for this is that the manner in which a star dies is determined by its mass at its formation. There are three possible deaths that a star can undergo. The most dramatic of these is the supernova, where the massive dying star, with masses greater than 5 times our Sun, or 5 solar masses, explode, seeding space with the raw materials to form new stars and new planets. It is in these explosions that the heavier elements are created and formed. A star whose original mass is between 1/2 and 5 solar masses will, when the fusible hydrogen in its core is consumed, expand to become a red giant, then collapse in on itself under gravity to become a white dwarf. This will be the fate of our Sun in about 5 billion years. And finally, small stars, less than 1/10 of a solar mass, will simply fade away after they run out of fusible fuel and become cold spheres of leftover hydrogen and helium. These little red dwarfs will simply cease fusion and cool into barely glowing brown dwarfs, and finally into cold black dwarfs. Since star death is determined by its size, we must ask, how much do stars actually differ in size, and why do these differences occur?
Sun is tiny compared to the really big stars out there. Eta Carinae, over 5 million times larger than our Sun. Betelgeuse, 300 times larger than Eta Carinae. If it was our Sun, it would reach as far out as Jupiter. And then there's this monster, VY Canis Majoris, the largest star ever discovered. 1 billion times bigger than our Sun.
Stars are formed in huge gas clouds or nebula in the galactic disk. So the answer to our question, how much do stars differ in size and why do these differences occur, is that large gas clouds produce large stars. This is because there is plenty of hydrogen gas to gather, or in other words to accrete, into large stars. One gas cloud may give rise to thousands of stars. Accretion is the process of growth or increase in size of an object by the gradual accumulation of additional matter. In this simulation, the small dust particles and gas particles of the nebula are represented by small dice which clump together. For stars, accretion is caused mostly by gravitational forces and to a lesser degree by electrostatic forces.
Gravity pulls the dust and gas into a giant, swirling vortex. Over hundreds of thousands of years, the cloud gets thicker and forms a giant spinning disk bigger than our entire solar system. At its center, gravity crushes the gas into a super dense, super hot ball. Pressure builds until huge jets of gas burst out from the center. Gravity keeps the pressure on, sucking in gas and dust particles that smash into each other, generating more and more heat. Over the next 500,000 years, the young star gets smaller, brighter, and hotter. Temperatures at its core reach 15 million degrees. Only at that mind-boggling temperature can atoms of gas begin to fuse together, releasing massive amounts of energy. And just like that, a star is born. It will shine for millions, even billions, or perhaps even trillions of years.
To summarize the events in the birth of a star. The size of the gas cloud or nebula determines mostly the size of the star that will form in it. The distribution of hydrogen in a nebula is not uniform, and it has areas of greater gas density. These areas will have greater gravitational forces. Within these massive nebula, some areas will begin to contract under the force of gravity. The areas of greater gravitational force attract more and more hydrogen from the cloud. These areas become in turn denser in hydrogen, and as such have greater gravitational force. They attract more and more matter. As these areas begin to contract, the local gravitational forces increase. This creates a sequence that in turn attracts more matter, leading to more gravity. So more hydrogen is attracted, giving more gravity, giving more hydrogen accretion, giving more gravity, and so on. As the cloud contracts, its temperature increases and it begins to spin. The rotation is due to conservation of angular momentum, and the increase of temperature arises because the cloud's volume has decreased. This means the space between the gas's atoms are closer, and they begin colliding with each other more often. It's these collisions that cause the gas cloud to heat. The combination of heating and spinning compresses the gas, which is mostly hydrogen, into a tight spherical, hot and glowing ball, surrounded by a flat disk called the accretion disk. The hot ball of gas at this stage is called a protostar, because it's yet to fuse hydrogen at its centre. It is from the accretion disk that planets will form at a later date. All the time, the protostar continues to accrete more gas from the surrounding accretion disk. It collapses further under its own gravity, getting hotter and hotter, as gravitational potential energy is transformed into the thermal energy heating the protostar. Eventually, the centre of the collapsing protostar heats enough for fusion of hydrogen into helium to occur at its centre. At this point, we now call the object a star. For fusion to occur, the following conditions are needed. Firstly, high temperatures. High temperatures mean fast-moving hydrogen atoms. It is high velocities that provide the hydrogen nuclei with the kinetic energy for them to fuse. Secondly, high pressure and density. When a huge number of hydrogen atoms occupy the same area, the chance of a collision resulting in fusion is increased. When the temperatures at the core of a star exceed 8 million Kelvin, the temperature and pressure become high enough to overcome the positive electrostatic repulsion of like-charged nuclei. This repulsion is called the Coulomb barrier. The radiant pressure created by the energy of fusion pushes outwards in all directions from the core. The outward force balances with the inward force caused by gravitational collapse. It is this inward force that continues to provide the core with the energy needed for ongoing fusion. These two forces will remain in balance until the fusible hydrogen in the core begins to run out. When the star's inward and outward forces are in equilibrium, the star is stable and is called main sequence, and it is fusing hydrogen into helium in its core. Zero-age main sequence stars, ZAMS, are newly formed stars that have just joined the main sequence on the Hertzsprung-Russell diagram. They are found on the lower edge of the main sequence band. The star will remain for most of its life as part of the main sequence, changing only slightly in temperature and luminosity as it ages. These small changes in brightness and temperature cause the star to migrate from the lower edge of the main sequence band to its upper edge. Once the star begins to run out of fusible hydrogen in its core, it will begin to undergo the process of star death and will leave the main sequence. From here it will undergo one of the three deaths that we began with. It could explode as a supernova. It could swell into a red giant and then collapse into a white dwarf, or fade gently into a cold black dwarf.
I would I were on yonder hill, it's there I'd sit and cry my fill, and every tear would turn a mill.